Hello, this is Dr. Hanaa Assil, and this is the second part of the review on Modular Unit 1. Remember, we said the IGCSE Chemistry Edexcel now has Modular Unit 1 and Modular Unit 2. So this is the second part of the review on Modular Unit 1. So what do we remember about the periodic table? We know that it is an arrangement of elements according to their atomic number. The part on the left is mostly metals, on the right it is mostly non-metals. You know that the number of the group indicates the number of electrons in outer shell. So anything in group 1, when we distribute its electron distribution, when we do the electron distribution, anything in group 1 will have 1 electron in its outermost shell, group 2 will have 2, and so on. So the number of the group is the same as the number of electrons in outer shell. Now, the number of the period indicates the number of energy levels. So anything in period 2 has 2 energy levels, period 3 has 3 energy levels, and so on. And we know that all elements in the same group have similar chemical properties. So everything in group 1 will have similar chemical properties because they have the same number of electrons in outer shell. Chemical properties are determined by the number of electrons in outer shell. So in each group, all the elements in that group have similar chemical properties. They do the same kinds of reactions because they have the same number of electrons in outer shell and the same, of course, electron distribution. We know that anything in group 1 are called alkali metals. That part in the middle are transition metals. The group 7 is halogens and group 8 is noble gas. So group 1 alkali metals, we know that they are in group 1, so they have 1 electron in outermost shell. They are actually the most reactive metals compared to the other groups. So that is why they have to be stored under oil. They're very reactive. They would react with the oxygen or water vapor in the air. They are soft metals. And as we go down the group, the one down is more reactive. So reactivity increases going down the group. And cesium is regarded as the most reactive metal. We totally ignore francium. It has other properties. So as we go down group 1, the reactivity increases. The density increases. But the melting point decreases. Remember, lithium is less reactive than sodium, less reactive than potassium. Cesium is the most reactive in that group. The reactivity and density increases down the group, but the melting point decreases. Why does the reactivity increase going down the group? We should realize that as we go down the group, the atom has more shells, more electrons. So the reactivity of a metal is related to how easily it loses its electron. So a more reactive metal loses the outer electron easier. So as we go down, more shells, so potassium, for example, compared to lithium, potassium has more shells. That outermost electron that we're trying to lose is further away from the nucleus, so less attraction forces between that electron and the positive nucleus, so the outer electron is lost more easily, and that is why we say potassium is more reactive. Transition metals, if we look at physical properties compared to the other metals, the transition metals are very hard, very high density, very high melting point. So comparing any transition metal with any of the other metals in group 1, 2, or 3, the ones in the transition will be harder, higher density, higher melting point. Remember, these are the physical properties. If we're talking about chemical properties, then the members of the transition metals are elements that can form colored compounds. They may act as catalysts, so they speed up the reactions, and they may have more than one oxidation state or valency, and we will be talking about that in the next part. So, physical properties, transition metals are harder, higher density, higher melting point than a metal like group 1. If we're talking about chemical properties, the transition metals form colored compounds, while the compounds of any metal in group 1, 2, or 3 will be a white solid. The metals, the transition metals, act as catalysts, have more than one oxidation state, and that is not the case with group 1. They do not act as catalysts, and they have specific oxidation states. Again, transition metals, their appearance are usually silvery in color. All metals are silvery in color except copper, which is reddish brown, and gold, which is yellow, and they have beautiful colors for their compounds. So if we say which element is used as a catalyst, remember that a transition metal is the one that will be used as a catalyst. Group 7, halogens. Halogens, fluorine, chlorine, bromine, iodine, astatine, they are all in group 7, so they have 7 electrons in their outermost shell. They are very reactive nonmetals. Now, which one is more reactive? Now, the one up is more reactive, so reactivity increases going up the group, and fluorine is the most reactive nonmetal. You need to know the appearance of halogens. Fluorine is a yellow gas, chlorine green gas, bromine reddish brown liquid, iodine gray solid, astatine is a black solid. So as we go down, it changes gas, liquid, solid. That means the melting point increases and the color gets darker. Iodine is unique because as a solid it's gray. As a solution dissolved in water, it becomes reddish brown solution in water, and when we heat the solid, it sublimes. It goes directly into gas with a violet color. Again, the most reactive nonmetal is the one up. But as we go down, the melting point increases, the density increases, and the darker the color gets darker. Now, we explain why is it that as we go down, the reactivity of a nonmetal decreases. This is because the reactivity of a nonmetal has to do with its ability to gain an electron. So, as we go down, the atom becomes bigger. The incoming electron that we're trying to gain is now further from the nucleus, less attraction force to the nucleus, so the electron is not gained easily. So the one down, iodine, is less reactive because the electron coming in is further away from the nucleus, less attraction forces to the positive nucleus, and less readily gained in the atom. Remember, the more reactive nonmetal displaces the less reactive nonmetal. So if I have chlorine plus potassium bromide, remember as a compound it is called bromide, but the chlorine is more reactive, so the chlorine will displace bromine. So instead of being potassium bromide, it becomes potassium chloride plus bromine. So chlorine plus potassium bromide gives bromine plus potassium chloride. Remember that potassium bromide is a compound of group 1, so it is a colorless solution. Now when we add chlorine, which is a green gas, the chlorine reacts, displaces bromine, so we get bromine in solution, is an orange, or as it gets darker it becomes reddish brown. So the color changes from a colorless solution to an orange solution due to the formation of bromine in solution. Again, chlorine plus potassium iodide. Chlorine is more reactive than iodine, so it will displace it. And potassium iodide, again, that's a compound of group 1, so it's a colorless solution. But when the chlorine displaces the iodine, now we have iodine in solution. Iodine in solution is reddish brown. Remember that the less reactive nonmetal will not displace the more reactive. So iodine cannot displace bromine. No reaction if we put iodine on potassium bromide. Why? Because iodine is less reactive than bromine. This is a typical question, 6 marks, where the question says a student mixes the following pairs of solutions: bromine solution, potassium chloride solution. Bromine solution and potassium iodide solution. Now explain how the student can use the results to show the order of reactivity of the 3 halogens. Remember, bromine is less reactive than chlorine, so it will not displace it. So if we add bromine solution to potassium chloride, which is a colorless solution, the bromine remains in solution, so actually the solution remains orange. This indicates that bromine is less reactive than chlorine and cannot displace it. But if we add bromine to potassium iodide, again, potassium iodide is a colorless solution, but now bromine is more reactive than iodine, so the bromine displaces the iodine. Now I have iodine in solution. This turns brown, and this indicates that the bromine is more reactive than iodine and displaces it. So the order of reactivity, which we should know, is chlorine more reactive than bromine, more reactive than iodine. Noble gases are the ones in group 0. They are monatomic gases. That means they are gases with individual atoms. The atoms do not join together to form molecules. They are unreactive or inert because they all have a full outer shell. So helium has 2 electrons, while that first shell takes a maximum of 2, so that first shell actually is full. Neon has 8 electrons in its outer shell, and so on, so they all have full outer shell of electrons. Remember that helium is used for filling balloons, argon is used for filling light bulbs since it is inert and will not allow the filament to burn. Neon is used for fluorescent lights. So if we say that we have a light bulb, it contains argon. So just why argon is more suitable than air, we fill this lamp with argon because argon is unreactive. It will not react with the filament, and it will not allow the filament to burn since it has a full outer shell of electrons, while if we put air, then that has oxygen, and this will cause the filament to burn. Helium is a noble gas. Which statement is correct? Remember, if the choices say helium has 8 electrons in its outer shell, no. Helium exists as diatomic, no. We said noble gases are monatomic. Helium is used as inert atmosphere in lamps, no. We don't use helium, we use argon. There are no naturally occurring chemical compounds of helium. Yes, because helium is inert, unreactive, so it will not react and form any compounds. Okay, if we say a metal that reacts violently with water, remember reacts violently, that means most reactive, and we said in the periodic table which metals are most reactive. They're the ones in group 1. Which of these is a noble gas? The one in group 0. A group 2 metal, of course, group 2, that's where the E is placed. halogen. A halogen is in group 7, so that is the halogen. In questions, we could be given the electron configuration and use that to determine which of these is a noble gas. Well, we look at the one that has a full outer shell. So E has 8 electrons in its outer shell. It's probably a noble gas. An element in group 4. How do I know if something is in group 4? If it has 4 electrons in its outer shell. The group number is the number of electrons in outer shell. An element in period 3. What do we mean by period 3? Period 3 means 3 energy levels. So I need something that has 3 energy levels. A monatomic gas. A monatomic gas is something that has a full outer shell, because that would be in group 8 or noble gas. You're also required to know how to write the chemical formula and balanced chemical equations. So how do we write chemical formula? Remember, if we're required to write the chemical formula of a compound, we write the symbols of each element and then put the valency of one under the other. Now, what do we mean by valency? Valency is the number of electrons lost or gained in order to have a full outer shell. So we know that anything in group 1 has 1 electron in its outer shell. It needs to lose that 1 electron to have a full outer shell, so we say the valency is 1. Anything in group 2 needs to lose 2 electrons. Anything in group 3 needs to lose 3 electrons. Anything in group 4 needs to lose or share 4 electrons. Now, anything in group 5 has 5 electrons in its outer shell. It needs to gain 3, so its valency is 3. Anything in group 6 needs to gain 2 electrons. The valency is 2. Anything in group 7 needs to gain 1 electron to have a full outer shell, so its valency is 1. But remember, there are things that are not in the periodic table, and you need to know their valency. So hydroxide is OH, valency 1. Nitrate is NO3, valency 1. Remember, the valency is the same as the charge on the group. So if I'm writing hydroxide alone, it should be OH minus, NO3 minus, NO2 minus. Ammonium is NH4. If it's standing alone, it's NH4 plus. But with a compound, we just write NH4 and its valency is 1. Carbonate, CO3, valency 2. Sulfate, SO4, valency 2. Phosphate, PO4, valency 3. Remember that the transition metals have more than one valency. So if we say iron, we have to be specific. Are we talking about iron that has a valency of 2 or iron that has a valency of 3? Now, copper that we work with is usually 2, silver is 1, and zinc is always 2. How do we write acids? We write H and then complete it according to which acid. So hydrochloric acid is HCl. Cl is in group 7, valency 1, and when we write, we do not write 1. So hydrogen valency 1, Cl valency 1, then it is HCl. Nitric acid is the acid that has nitrate. Sulfuric is the acid that has sulfate. Remember, valency of sulfate is 2, so you put 2 under the H. Phosphoric is the acid that has phosphate, valency 3, so it's H3PO4. Carbonic acid is the acid that has carbonate, valency 2, so this is how you write the formula. In some cases, the name includes mono something, di something, tri something. Mono means 1, di 2, tri 3. So nitrogen monoxide is nitrogen with 1 oxygen, and you forget about thinking about the valencies. We do not These are exceptions to the idea of putting the valency of one under the other. Forget about the valencies. Mono means one oxygen. Di means two oxygens. So nitrogen dioxide is NO2. Carbon dioxide is CO2. Trioxide means three oxygens. So SO3 is sulfur trioxide. And then we should know how to write balanced chemical equations. So when we have we're required to write, first of all, if the question says write a chemical equation, that means it has to be simple and it has to be balanced. If the question requires word, it will tell you word. If we do not mention word, then the question does not want a word equation, it wants a balanced symbol equation. So we write the formula and then we balance the equations. If we're required to write state symbols, remember that something that's a solid, I have to include that it has S, that's a solid, L, liquid, G, gas. Aqueous means dissolved in water. So it is a substance that dissolved in water, then its state is aqueous. Remember that some molecules are diatomic. So if I say diatomic means two atoms together, they cannot stand up as one. So if I say something plus hydrogen, I have to write it H2, nitrogen, N2, oxygen, O2. Any of the halogens will be diatomic, F2, Cl2, Br2, and I2. So if we're required to write an equation for this, now the one that is written out there, that is the word equation. Remember, word equation is not something that's balanced. But when we want to write a symbol equation, we said nitric acid is HNO3, calcium hydroxide, calcium is in group 2, so the valency is 2, so the 2 goes under the hydroxide, and hydroxide is valency 1. Calcium nitrate, again calcium valency 2, I put 2 under the nitrate. The nitrate is valency 1, I don't put anything under the calcium. Plus water, you cannot leave an equation without checking its balancing. So to balance the equation, we count the atoms on both sides of the arrow and increase the one that is less. So if we say how many calcium, for example, before the arrow I have 1 calcium, after the arrow I have 1 calcium. How many hydrogens? Now before the arrow I have 1 in the HNO3 and 2 in the calcium hydroxide. So I have a total of 3 hydrogens. Before the arrow, I have only 2 hydrogens. After the arrow, I need to increase the one that is less. So that means I need to put 2 in front of the HNO3 because that will give me 2 nitrogens, and 2 in front of the water, so that now I have 4 hydrogens after the arrow, and a total of 4 hydrogens before the arrow. Barium chloride, barium is in group 2, so it's BaCl2. Sulfuric acid, again, acid starts with H, valency of sulfate is 2, so it's H2SO4. Plus barium sulfate, now barium is valency 2 and sulfate is also valency 2. So they cancel each other. So that's why barium sulfate is BaSO4 plus HCl. Again, to balance, we count before the arrow and after the arrow. So obviously I have 2 chlorines and 2 hydrogens before the arrow. So I need to put 2 in front of the HCl. Remember that any number before the formula applies to everything after it, so that means now I have 2 hydrogens and 2 Cl's after. So to balance this equation, for example, we count before the arrow, after the arrow, and increase the one that is less. So before the arrow we have 2 carbons, so I need 2 carbons after the arrow. Before the arrow we have 6 hydrogens, so I need 2 times 3 to give 6 hydrogens. Now how many oxygens now after the arrow? We have 2 times 2, that's 4, plus another 3, we have a total of 7 oxygens after the arrow, so I need 2 times something. Well, you can write 3.5. 2 times 3.5 will give 7, but usually we do not write halves. We double the numbers, so that now I have 4 carbons, 6 hydrogens. Now how many oxygens after the arrow? I have 2 times 4, 8 plus 6, that is 8 plus 6, 14. You 2 times 7, that is a balanced equation. Again, this is an equation that usually we're asked to write because we're going to use it in organic chemistry. Glucose is C6H12O6. Now this gives ethanol. How do we write ethanol? We will remember that ethanol is something that has 2 carbons and an OH. This is an alcohol. Carbon dioxide. So this is how we write it. C2H5OH, ethanol. Plus carbon dioxide, of course, and then we need to balance. So we have 6 carbons before the arrow. That means I need to increase these carbons. But first we have 12 hydrogens, so I must put 2 here so that I have 2 times 6. You can see that that's 6 hydrogens. H5 plus another H, that's 6 times 2, that's 12. So I need to put 2 here to balance the hydrogens, and that means now I have 4 carbons there. I need a total of 6, so I need 2 here. Now if you check the oxygens again, please leave the oxygens till the end. Usually when we balance everything else, usually the oxygens are balanced. So now I have 2 plus 4, that's 6 oxygens, so now it is balanced. Ammonium sulfate is prepared by reacting ammonia with sulfuric acid. We should know that ammonia is NH3, sulfuric acid is H2SO4. This gives ammonium sulfate. Remember, valency of sulfate is 2, so I need to put 2 under the ammonium. Valency of ammonium is 1, and that means to balance I have 2 nitrogens after the arrow. I need 2 nitrogens before the arrow. If you check the hydrogens, now after the arrow I have 2 times 4, that's 8 hydrogens. Before the arrow I have 2 times 3, that's 6, plus 2, 8, and 1 sulfur and 4 oxygen, so it is balanced. Here the question says give chemical equation for reaction between cesium and water, and we should know cesium plus water gives cesium hydroxide plus hydrogen. So we write the symbol equation first, and then we need to balance. 1 cesium before the arrow, 1 cesium after the arrow. Now 2 hydrogens before the arrow, we have a total of 3 hydrogens after the arrow. That means I need to increase the one that is less. Increasing means instead of having 1, which we don't write, we write 2. Now I have before the arrow a total of 4 hydrogens and 2 oxygens, so I need to fix the oxygens. If I put 2 here, now I have 2 oxygens and a total of 4 hydrogens, but we have ruined the cesium, so we need to put 2. Sometimes we are required to write the state symbols. So here, for example, I need 2 here to fix the hydrogens because I have 3 hydrogens after the arrow. I need to increase the hydrogens before the arrow, but that means now I have 2 oxygens before the arrow, so I put 2 oxygens. After the arrow, I've ruined the sodium, now it's balanced. Now sodium, what is the state symbol of sodium? Of course, sodium is a metal, so it's solid, so we put S. Water, we always put liquid. Sodium, anything is something that's soluble in water, so the state symbol is AQ, aqueous, dissolved in water. And of course, hydrogen is a gas. Okay, chemical calculations. Let's go through very quickly what we learned about basic calculation, calculating molecular mass or MR of a compound, we write the formula first. So if we're writing magnesium phosphate, remember that phosphate is PO4, valency 3, so we put 3 under the magnesium. Magnesium is in group 2, you put 2 under the phosphate, and then you look at the periodic table and determine the mass number of each one. Remember, the mass number is the bigger number. So magnesium has a mass number of 24. We have 3 of them, so that's 24 times 3 plus the phosphorus. How many phosphorus do we have? Anything outside the bracket applies to everything inside the bracket. That means I have 2 phosphorus. And oxygen, how many oxygens? 2 times 4, that's 8 oxygens. Aluminium sulfate, again, aluminium is in group 3, valency 3, it goes under the sulfate. Sulfate has a valency of 2. Now, looking at the periodic table, we have 2 aluminium, each of them has a mass number of 27, so that's 27 times 2, plus the sulfur times how many? We have 3 sulfurs, and we have 3 times 4, that is 12 oxygens, and you add all that up, that is the MR. And then you should know that the empirical formula is the formula showing the simplest ratio between the elements. So I can say the ratio is 1 to 3, so the empirical formula is CH3, or 1 to 4, so CH4, but the molecular formula is the formula showing the actual ratios between the elements. So that could be C2H6, so that would be a multiple of the empirical formula. So it's the empirical formula times 2 or the empirical formula times 3 that gives the molecular formula. And you should remember to determine empirical formula. So let's say we're trying to determine empirical formula. You will be given percentage or masses. So we could say we have 80% carbon, or in grams, we deal with it in the same way. We write it like this, the percentage of each one, and we go through 2 main steps. Divide by mass number. So that first one would be carbon divided by 12, hydrogen divided by 1. Now what comes out, we're going to divide by the smallest of it. Which of these is the smallest? 6.67, 6.67. That gives a ratio of 1 to 3. That means the empirical formula is CH3. Please don't stop at the ratios. We're required to write out the empirical formula. So if it is 1 to 3, that means it is CH3. Now, if we're required to determine the molecular formula, we will be given the molecular mass. So let us say that the question says, okay, we got the empirical formula is CH3, but the question says that the MR of that compound, or the molecular mass of that compound, is 30. So what is the molecular formula? Well, we determine the molecular mass of the formula we got. So we got that the empirical formula is CH3, so its MR is 12 plus 3, that's 15. But we are told that the actual molecular mass is 30. That means actually 30 has 2 of these, and that means that the actual molecular formula is the empirical formula times 2. So instead of CH3, it is actually C2H6. Again, what is the empirical formula of the oxide formed when this grams of chromium produces this grams of chromium oxide? Remember, that means that I'm starting with chromium, it's 2.6 grams. Now, if the oxide total is 3.8, that means the oxygen alone would be the rest of the 3.8. So the oxygen is 3.8 minus 2.6, that's 1.2. Again, divide by the molecular mass of each one. What comes out? Divide by the smallest. But in this case, when we divided by the smallest, we got a ratio of 1 to 1.5. Please do not round up that 1.5. We don't round it up. We don't write it as 1, or we don't write it as 2. We have to multiply by a number that changes it into a whole number. So instead of 1.5, I'm going to multiply through by 2, everything by 2. So instead of 1 to 1.5, it is 2 to 3, and that means that the formula is Cr2O3. When the ratios are 1.5 or 1.4 or 1.6, you have to multiply by a number that gives a whole number. You don't round it up, and you multiply through all the ratios by that number. So if I have this, an alkane contains this carbon and this hydrogen, and we're told that the molecular mass of the alkane is 58. So let's do the empirical formula first. Divide by the mass number, the numbers that come out, divide by the smallest. Well, when we did this, again, it gave 1 to 2.5. Don't write it as 2 and don't write it as 3. You multiply through by 2, so it is C2H5. Now, we're told in the question that the MR is 58. That means I need to get what is the MR of this that I got. The C2H5 has an MR of 29. We're told it should be 58. That means it is twice of what we got. So instead of C2H5, the molecular formula is C4H10. Again, sometimes we will have hydrated salt. Hydrated salt is something that has water in its crystal. So MgSO4 X water, and we're trying to get what is the X. So we are told that it has 12.04 grams of the MgSO4, and that means that the rest of the 24.64 is the water. And that means you treat it as if you're getting empirical formula. The magnesium sulfate alone is 12.04. The water is the rest of the total hydrated salt. So 24.64 minus the 12.04. So that's 12.6. Again, divide by the MR. The numbers that come out, divide by the smallest. And this gives me the ratio, so it's 1 magnesium sulfate to 7 water, so that is the formula, or X is equal to 7. And you should know that a mole is the relative atomic mass in grams. So the MR of something in grams, that's 1 mole. So sodium, for example, 23 grams of sodium is 1 mole. Now, how to calculate the number of moles? We said we have equations that you should know. So if we're given a mass in grams and we're told to calculate number of moles is mass in grams over the molecular mass, or the MR. So number of moles is mass over molecular mass. If we're required to get the mass, for example, you should be able to rearrange the equation. Mass is number of moles times MR, or MR is mass over number of moles. Now, if we're talking about gases, number of moles is the volume over 24. This is at room temperature and pressure, or RTP. So when he says RTP, I can use number of moles is volume over 24. Remember, the volume has to be in decimeter cubed. If we are given the volume in centimeter cubed, you need to divide by 1,000. So number of moles is volume over 24 for gases. And if we're required to get the volume, then the volume is number of moles times 24. But if we're talking about solutions, the number of moles is concentration times volume. Again, the volume has to be in decimeter cubed. Centimeter cubed, you divide by 1,000. So number of moles for a solution is concentration times volume. That means concentration is number of moles over volume, or volume is number of moles over concentration. We should also know that we have Avogadro's law that says in 1 mole there is 6.02 times 10 to 23 molecules. So this is called the Avogadro constant. And if I have 1 mole and I'm trying to get the molecules, The number of moles is the number of molecules over the Avogadro's constant, 6.02 times 10 to 23. That means number of molecules is number of moles times that number. Usually you're given an equation and you're told to get something from the equation. So let's say we have this equation and we are required to get volume of HCl if I'm starting with a certain information about something. So here we're told 5.3 grams of sodium carbonate. We're given information about sodium carbonate. The first thing that we do is get number of moles. How do we get number of moles? Well, we're given 5.3 grams. That means I'm going to use which equation? The number of moles is mass over molecular mass. The mass we're given over the MR, you add it all up, this comes out to a certain number of moles. Now we're asked about what? About HCl. We look at the equation. So the first step, get the number of moles of whatever information we're given. Then we're asked about HCl. We look at the equation. What is the relationship between number of moles of sodium carbonate and number of moles of HCl? Remember that the balancing in the equation is a relationship between the number of moles. So the equation says if the number of moles of sodium carbonate is 1, the HCl is twice of that. So number of moles of HCl is twice the number of moles of sodium carbonate. Then we get what we're asked. We're asked to get what? Volume of HCl. Which equation should I use? HCl is a solution. So the volume of the solution is the number of moles over concentration. The number of moles we got, the concentration we are given, the answer for volume here comes out in decimeter cubed. If we're required to get it in centimeter cubed, multiply by 1,000. Another question. Here we're given 25 centimeter cubed of potassium hydroxide. Was neutralized by a certain amount of sulfuric acid. And first thing we're told to get number of moles of potassium hydroxide. Well, which equation do we use again? We said we're given here a solution, volume, concentration. So we're using that third equation. Number of moles is concentration times volume. Again, the volume is given in centimeter cubed. I have to divide by 1,000 before I can use it in the equation. So this is number of moles of KOH. Then we're required to get number of moles of sulfuric acid. We look at the equation. The equation says 2 moles of potassium hydroxide react with 1 mole of sulfuric acid. That means number of moles of sulfuric acid is half that of KOH. And then we're required to get concentration of the sulfuric acid. Concentration is number of moles over the volume. Again, we're given volume of sulfuric acid in centimeter cubed. I have to divide by 1,000 before I put it into the equation. Okay, in this question, calcium hydroxide reacts with HCl to give calcium chloride plus water, and we're required to calculate number of moles of HCl. Again, what are we given? We're given volume and concentration. So we use number of moles is concentration times volume. Remember, volume again has to be divided by 1,000. Then we're required to get the mass of calcium hydroxide. Well, how do we get the mass? You should realize, first of all, we need to get the number of moles from the equation. So if we have number of moles of HCl, according to the equation, the number of moles of calcium hydroxide should be half of that. And then mass is number of moles times MR, and that is the answer. We will also be required to calculate percent purity. Percent purity is the mass of the substance that we calculate is supposed to be there over the total mass of the impure substance times 100. So for example, here we have 1.23 grams of impure barium carbonate. We cannot use that mass for anything. We're given volume of carbon dioxide is 0.12 decimeter cubed, and that can be used to get what was the number of moles of barium carbonate. So first of all, we get number of moles of carbon dioxide. Carbon dioxide is a gas. We have the volume. So the number of moles of carbon dioxide is the volume over 24. And then we look at the equation. From the equation, the number of moles of the barium carbonate compared to the CO2 is exactly the same. Now we have number of moles of barium carbonate. Then the mass of the barium carbonate is the number of moles times the MR without. In this question, we're given 1.23 grams of impure barium carbonate. So we don't really know what is the mass of barium carbonate, so we cannot use that for anything. But we are told that the volume of carbon dioxide collected when it reacts with HCl is 0.12 decimeter cubed. Remember, we just say RTP, room temperature and pressure, in order to be able to use the equations that we have. So we are told to get the percent purity. That means we need the mass of barium carbonate, and that means I need to use that volume of CO2 to get number of moles first. We're given information about CO2, volume of a gas. So which equation do we use? We use the one that is volume of gas, number of moles is volume over 24. So that is the number of moles of CO2. And then we look at the equation. What is the relationship between the number of moles of CO2 and barium carbonate? They are the same. So number of moles of barium carbonate is the same. Then we need the mass of the barium carbonate. Mass is number of moles times MR. That means actually we had 0.985 grams of barium carbonate, not 1.23. So the percent purity is what we calculated, the actual amount of barium carbonate that is in there, over the total of the impure times 100, that is percent purity. To calculate percent yield, again, we do an experiment in the lab, we get a certain amount of mass, but usually it is less than what we should get, the theoretical yield. So the actual in the lab is usually less than the theoretical. So to get percent yield, we calculate the theoretical, and then what was actually obtained over the theoretical times 100, that is percent yield. So if we have 4.8 grams of hydrogen, reacted with excess nitrogen to give 12.8 grams of ammonia, what was the percent yield? Well, we should calculate how much ammonia we should get. That's what we call theoretical. So using the 4.8 grams of hydrogen, again, we get number of moles of what we're given information of. So number of moles of hydrogen, mass over the molecular mass of H2. So that is number of moles of hydrogen. And then we look at the equation. What is the relationship? Obviously, from the equation, 3 moles of hydrogen give 2 moles of ammonia. So if I have 2.4 of hydrogen, how much ammonia? So that is 2.4 times 2 over 3, that's number of moles of ammonia. And then we need to get the mass, number of moles times MR. That is what we should get. That is the theoretical mass. So the percent yield is what they actually got, 12.8, over what they should get, the theoretical yield that we calculated, times 100. When given information about both reactants, we need to decide which one is excess, which one is too much, because we're not going to use that for any calculations. We're going to use the other one, which is not excess, and that is called the limiting reactant. So here we're given information about both nitrogen and hydrogen, and we're asked about ammonia. So am I going to relate it to nitrogen or to hydrogen? I need to decide which one is not excess. So if I put 50 grams of nitrogen, the number of moles is the mass over the molecular mass. Now, if I look at the equation, number of moles of hydrogen should be 3 times of that. So actually it should be about less than 6 grams or something. So if we calculate the amount of hydrogen that they put, the number of moles of hydrogen that they added was 20 mole. We needed only 3 times of the nitrogen. So obviously the hydrogen is too much. The hydrogen is excess, and that means we do not use the information about the hydrogen. We use the information about the nitrogen. So now I'm going to relate it to ammonia. 1 nitrogen gives 2 ammonia. So the number of moles of ammonia is twice that of the limiting reagent, which is the one that's not excess. That is number of moles of ammonia. So if we're required to get the mass, that is number of moles times the MR. So this question says calculate the mass of carbon dioxide given off when 20 grams of calcium carbonate react with this volume and this concentration of HCl. So we're given information about both reactants. First, we need to decide which one is not excess, which one is limiting, so that I can use it to calculate the CO2. So we get the number of moles of each one. So number of moles of calcium carbonate, this is mass over molecular mass. Now number of moles of HCl, this is a solution concentration times volume. From the equation, the number of moles of HCl should be twice the calcium carbonate. Actually, it is much less than the calcium carbonate. That means that the calcium carbonate is excess, and I'm not going to use it for any calculations. We need the number of moles of HCl because the HCl is the one that is limiting. It's not excess. So I compare it to the CO2. Now the number of moles of CO2 is half the number of moles of HCl, and I can get the mass, that's number of moles times. This is another type of questions in which we're told that complete combustion of 1 mole of an alkane, if you remember, alkanes have carbon and hydrogen only, produces 396 grams of carbon dioxide and 180 grams of water. What is X, Y, and Z? What's the number of moles of oxygen needed to react with the alkane, and the number of moles of carbon dioxide, and the number of moles of water. And from that you can tell the formula of the alkane. So according to this, if we have Y of CO2, that is the number of carbons. And if we have Z of H2O, that means the number of hydrogens is 2 times Z. So we can get the formula of the alkane from getting the number of moles of each of these. So number of moles of carbon, this is the same as the number of moles of carbon dioxide. So carbon dioxide is mass over molecular mass. This gives 9 moles of carbon. So that means Y is 9. Now number of moles of hydrogen is twice that in water. Remember, if we have number of moles of water, the number of moles of the hydrogen in the alkane is twice of that. So number of moles of water is again the mass over the molecular mass of water. So 20 is the number of moles of hydrogen, and that means my formula was C9H20 to give 9 moles of CO2 and 10 moles of water. Of course, to balance, then the number of moles of the oxygen would be 14, and that is the value for X. This is another kind of question in which we have the diagram represents an atom of an element, and we're told, and we should know, that 1 mole of the element contains Avogadro's number of atoms. So we have 6 times 10 to the 23 atoms. Calculate the number of electrons in 1 mole of atoms. Of course, if we look at that diagram, each atom has how many electrons? It has 12, so the number of electrons would be 12 times the total number of atoms, which is the Avogadro's number, and this gives this number of electrons. Okay, we're going to stop here for this part of the review. Please make sure you study all of this, and we will continue the rest of the chapters in the next part of the review. Thank you for listening.